Hello everyone, this is video 14.6. We're going to be looking at dilations and similarity. So section 14.5 was on similarity, so we're continuing looking at similarity, but within the context of this new thing called dilations. So we'll define that, we'll connect that to a lot of the stuff we've already looked at in this chapter, and look at some problems involving dilations and similarity. So let's get started. We have our last transformation now that we need to look at, and that is the dilation. And this dilation is in addition to the transformations that we've looked at previously in this chapter, the translation, reflection, rotation, and glide reflection. So in addition to those four. We have our original object here, this ABC, this triangle. Now, to do the dilation, what we really need is a fixed point. So we're going to do this dilation with this object and this fixed point. And what we're going to do is we're going to connect this fixed point to the points of our object, and then we're going to continue this out along these rays. And so we're going to form these objects, these points here, and these are the image points of our original object. And you can tell they're the image points because they've got the little apostrophe there. So we got our A prime, B prime, and C prime, and that forms our image. Now, these two shapes are going to be similar to each other, and they're going to be constructed in such a way that these 2 points or these two shapes are going to be similar. We could put this point here at A prime and this point over here at C prime, like over here, and then it would be at this kind of weird angle and it wouldn't work. So we're going to look at sort of the rules of construction around this, but essentially we can see that these are all going to be parallel. And so we can see that this side is parallel to this side, this horizontal side is parallel to this horizontal side, and then this hypotenuse, what looks like a hypotenuse, is going to be constructed parallel here. So if we just take 3 random points on these rays, we're probably not going to get something that is similar. We're not going to get a dilation. So it's a little bit more restricted than this. But once we construct it along the correct lines, if we do it the right way, we get the right shape. Pretty straightforward. And so this is going to give us our dilation. So this is a transformation, but hopefully it's obvious why this is not a rigid motion. Because remember, a rigid motion is not going to change the size or shape of the object. So, and we're not changing the shape. We're going from a triangle to a triangle, but we're clearly changing the size. You feasibly could do the dilation with a scale factor of 1 and keep the object the same. But because of the idea of this fixed point, it would be moving somewhere, probably to the exact same spot. So if we did a dilation that kept it the exact same shape, we would either be doing a translation or we would be keeping the object in the exact same place. So like our 0 degree or 360 rotation. So typically we don't talk about those as being dilations. We want them to sort of like move around, beginning bigger or smaller. So these transformations are going to allow the shapes to be similar, but they're not going to be congruent. Rigid motions require the shapes be congruent, and remember, everything that's congruent is also going to be similar. So you may want to go back and look at the rules for similarity and congruency if that sentence doesn't make an awful lot of sense. But similar objects are not always congruent, but congruent objects are always going to be similar. And these transformations that we're going to be looking at in this section are going to produce similarity, not congruency. So let's look at an example of how we could construct a figure. So we've got this triangle here, PQR, and we want to do this dilation around this point at the origin, at the point 0, 0. So what I want to do is I want to make this twice the size. I'm going to construct this ray. And so I'm going to construct this ray going from O through P and then up like this. That's not the straightest line I've ever drawn. But if I look at this point and this point, I can see that I'm going up 3 over 1, up 3 over 1, up 3 over 1. So I'm going to use the slope of this line to sort of help determine where I should be going. Now, I want this to be twice as big. So this point P, which is at 1, 3, is going to become this new point at 2, 6. And so you can kind of see this red triangle here sort of gets duplicated up here. So I'm continuing this slope, this up 3 over 1 slope to get this point here, P prime. Now I'm going to do the same thing with this Q, and this Q is going to go over 3 up 1, over 3 up 1, over 3 up 1, and continue. This point Q is at 3, 1, so you can probably guess Q prime, the image of that Q, is going to be at 6, 2. So again, I'm using, I want to go twice its size. My scale factor is 2, so I'm doubling everything. So again, this triangle sort of gets applied over here, and I get this point here for my Q prime. Now, if I do this R, this is pretty direct. This is 45-degree angle cutting through here. And so then this point R, this 1, 1, is going to go to R prime at 2, 2. So it's going to go here. Now, if I connect all 3 points here, here's my R prime. Well, I can look at my PR, and I can see the length of PR is 2 units. If I look at the length of P prime R prime, I can see that's 4 units. And so I've done what I wanted to do. I've made this triangle twice as big. So I've gone from 2 to 4. I've gone from 2 down here to 4 here. Now, we haven't really talked about how to find this length exactly. We talked about using the Pythagorean theorem. We haven't really talked about square roots all that much. So I'll leave this as an open problem if you want to verify. But we can see that this side is parallel to this side. This horizontal is parallel to this horizontal. The sides have doubled in size, the ones that I can find. So it's reasonable to assert that this one's going to be twice the size as well. I can show the similarity. I know that the scale factor is there. It's provable if we need to prove it, or we could take it by similarity. Okay, so we saw this idea earlier that angle, angle, angle doesn't give congruency. And we just sort of left it at that when we were talking about triangle congruency. But it does do something. It tells us similarity. So if I see two triangles like these two, where the angles are all congruent, but it's pretty clear that the sides are not. So if I look at this BC, so side BC is between the 54 and the 85. And so side QR is also between the 54 and the 85. Now, I can't call them congruent because clearly BC is shorter. So what I can do is just say that they're similar. And I use this little, this tilde here to show that they're similar to each other. So they are in proportion. So I don't know the length of QR. I don't know the length of BC, but I do know that they're going to be in the same ratio. So I could say BC, the length of BC is to the length of QR as, so now I could look at these longer sides here, as the length of AC is to the length of PR. So I don't know what the lengths are necessarily, but I know that the lengths are in that constant proportion, that they hold the same ratio, and so I can show similarity, or I can show that as a result of the similarity. So if I have that fixed point and I can see the dilation, that shows similarity, but also knowing the angles are all congruent also will show similarity. So I kind of alluded to this in a previous problem, but I want to make this a little bit more clear, as I think it's a really important conceptual point, that this idea of similar triangles and this constant ratio, this constant proportionality, really ties into the idea of slope. So we've got three triangles here, but really I'm just going to focus on the green one and the pink one. And so if I were to take this length right here, I can see that the slope of this is going to be the change in y, so it's going up 2, so 2 minus 0 over the change in x, so 3 minus 0. So I see the slope here is 2/3. Now, if I look at this pink triangle and go between these 2 points here, then I can do the same slope calculation. And so my change in y, I've gone from 6 down to 5, 4, 3, 2. So I've gone 6 minus 2. And then my change in x is going to be 9, 8, 7, 6, 5, 4, 3. So 9 minus 3. So this slope between these 2 points is going to be 4/6, which reduces to 2/3. So hopefully you know that whenever we're trying to evaluate the slope of a line, it doesn't matter which 2 points I take, I'm going to get the same slope no matter what, again, assuming that, given that it's a straight line. The reason this is the case is because all of these triangles are similar. So we can see here that this green triangle is going to be similar to this pink triangle. I can't know why I can't draw a straight line right here. So it's going to be similar to this, there we go, this pink triangle. And we can see why. These are all going to be dilations off this point. And so this point is carried along this ray. And then we see that these sides are all going to be parallel here. And so we've got similar triangles. These are going to be parallel to them, so they're part of the same line, so they have to be parallel. So the idea behind this, why this slope stays constant no matter which 2 points I pick, is an extension of this idea of similar triangles and proportionality. So I want to look at a couple of problems and look at some really common mistakes that students make in doing these problems. And so this problem here, we want to find this length of x. So we want to find this missing length. And so one way we could do this would be to set this up by similar triangles. But in order to do that, I got to be able to show that these are, in fact, similar triangles. So one thing that really helps in solving this problem is to draw these two triangles out as separate triangles. And this will help us get around a lot of confusion. So if I look at this angle and this angle, I know they're congruent because they're both right angles. So I can tell that. These dots are meant to show that these angles are congruent. So I'll put my 1 mark angle in there. So now this angle is congruent to this angle. But now, how do we know that these two angles are congruent? And this may seem like a really obvious point, but a lot of students will overlook this because we've taken these two triangles and drawn them out into two separate triangles. In this figure, we can see that angle A is obviously equal to angle A. And this is an opportunity where we can say not just congruent, but actually equal because they are actually the same angle. This is angle A in both these triangles. And so now I've got all three angles are going to be pairwise congruent. I got right angle to right angle, angle 1 to angle 1, angle 2 to angle 2. So I know these two triangles are similar, and I can now start to solve this proportionality. Now, if I label these sides, this is an X and this is a 3. This is a 6. A really common mistake for students to make is to label this side here 4, because they're just looking at X is to 3 as 4 is to 6. And hopefully you can see how that's incorrect, because this whole length here is actually going to be X plus 4. It's these two lengths taken together. It's not just the 4. If we were to do X is to 3 as X is to 6, we're actually comparing that triangle to that trapezoid on the bottom, which is not the problem, and also doesn't work. So we got this as going to X to 4. So my proportion now is going to be this side is to this side, X is to X plus 4, as 3 is to 6. Now this is using our external scale factors that we looked at earlier. I could also set this up as X is to 3 as X plus 4 is to 6 if I wanted to use internal scale factors. So either of these are going to work. Now, I'm going to leave the problem here because if you haven't done any algebra with proportions in a while, if you're taking 138 before 137, then maybe you haven't seen this in a while. It's not really necessary to do right now. I will say that you need to know it by the end of the 137, 138 sequence, but I don't want to go into this if people haven't seen it necessarily. So, yeah, I'll leave this as an open problem. If you have questions about this, some of the problems that we'll see later on in class won't have two variables like this, but I just wanted to introduce this problem because it's a really common one and one that you'll see. I also wanted to look at this problem because it's another really common problem, and you'll see the similarity with the previous problem here in a moment. The setup of the problem is that we've got this fixed point here, and we've got a person who we know is 6 feet tall. We're in Canada apparently, but I'm going to guess this person is not 6 meters tall. So we have this person here that's 6 feet tall, and then we've got a flagpole over here with some height h. We don't know what this height is. We do know that the person is 3 feet from this fixed point, and we do know that the flagpole is 20 feet from the fixed point. And a really important part of this is that from this point to the top of this person's head, to the top of the flagpole, these points are all collinear. They are all on the same line. So what we want to do is use this information to find the height of the flagpole. The setup of this problem is almost identical to the previous problem. The only thing that's different really is where the variable goes. You can see we've got our two triangles here. We've got our little triangle and our big triangle. The little triangle is our person, so we've got our 3 to 6 internal scale factor, and then we've got our big triangle, which is our flagpole, so 2 feet to h feet. Now, this problem we can do without sort of the messier algebra of the previous problems. I got no problem going ahead with this. I know that this this side here, this is absolutely not drawn to scale because the way these triangles are set up, the 3 is longer than the 6. But we've got our long, quote unquote, side is twice as much. So if this is 20, then we know that the flagpole has to be 40. Again, I really recommend for students who are struggling with this to draw this out as two separate triangles. We can see how everything matches up. I know that these are right angles because we're assuming the flagpole was built at a right angle, and we're going to assume this person has some degree of balance. So we know that they form a right angle. And then we know that this angle is going to be congruent to this angle because we've got parallel lines cut by the transversal. And lastly, we know that this angle is congruent to itself because everything's equal to itself. So very similar setup to the previous problem. The solution's a little bit cleaner, but another really common application of this, estimating the height of something using similar triangles. So for our checkpoint problem, I want to do a dilation of this triangle from this point here, this negative 6, 0. And so I'll get you started. We'll connect this up here to this C and then do the ray from that. And I want to do a 1/2. I want to make this triangle, the image of this half as big. And so from here to here, I'm going to go this midpoint, and that'll give me the half. So here's my C prime. So I'll get you started there and give you the C prime. You need to find the A prime and the B prime, connect those points together as best you can, and then make sure that what you get is, in fact, half of that original triangle. If you have any questions about this problem or anything else from this section, as always, bring those questions to class, and we'll get them answered. All right, thanks.